Hello everyone, welcome to another problem session. So today's problem comes from 2020 JEE Advanced Phys paper 1. We are doing all the other problems this week. Alright, so this is there's a little bit of misspelling here. Check out, and this is physicsbootcamp.org. Alright. If you like this video, we can hit a like button, etc. So that's just advertisement. All right, so here is a question. It's a kind of little tricky question, because if you just memorize some formulas, you have to memorize some formulas and why those formulas are correct. But then you have to derive the answer, and all four may be right, one may be right, two of them may be right, three of them may be right. Any combination of this may be right. So you have to check each of the answers. So there are two kinds of answers here. One is for R and V, another is for E is energy. So the problem is about, let's read this. Particle moves in a circular motion. So we have a circular motion, and this were the center. So this distance from that is little r, and potential energy, this is not potential, but potential energy that this feels is F times R. F is a positive constant. So if you look at this, VR is FR. That will mean force, and so this mass is m, say, okay? Particle's mass is m. So F on m will be minus del of potential energy. When you work this out, it's going to be minus r hat F. So F is actually is force, and it's pointing towards the center in a radial coordinate. R hat is that direction. Of course, in different places are a different direction, right? It's radially out from the center. So this force is radially inward, magnitude is F. That's what this means. Its energies are calculated using Bohr model. So this is saying use the Bohr model. So you have to know what the Bohr model is. So Bohr model is, if this is one of the orbits, say this is nth orbit, and this m and is going in a then I'm going to just say this r sub n, and let's the speed is v sub n minus this orbit. So the Bohr model is basically this statement: m v n r n. So this is the angular momentum, is some number n, that number n times h bar. H bar is n h over 2 pi. So this is Bohr model, okay? Everything else you can that uses this becomes the equation, like energy uses this, R uses this, V uses this, then that becomes a predictions of the Bohr model. All right. And the energy will simply be half mvn square plus the potential energy for R equals to Rn. So this is a Bohr model, and I can kind of make this guy mvn in here and make it more like half. So it's a square, so n square h bar square over Rn square, kind of like this, right? So I can use this plus v Rn. So that will be like one way you can say energy will be written. and Vrn will be just F. So this will be F times Rn for this thing. If you have some other model for potential energy, like electrostatic potential energy, then this formula will be different. So that's how energy gets its independence. You have to add these two together. All right. If the radius particle, so this in this equation, in this question, Rn, R is for Rn, and V is for Vn, and this energy, the nth orbit, E is En. Okay, so how do we check these, which way the R will go, which will the other things will go? Okay, so in addition to this, in order for us to make progress, in addition to these equations that we have it over here, you also have you have a circular orbit. So that's going to be like F mvn square Rn. So that just mean mvn square equals to Rn times F. So over here, actually, I could have done half Rnf for this whole thing, and this thing will be plus Rnf. So this is 3/2 Rnf. Okay, so I could have energy would be like this, and it will be useful when we write like this. So if I have to figure out what Rn is, and then I'm done, right? Okay, so how do we get Rn? Let's try to use this together, and then it will become very clear how to get Rn. But this is Vn square, so I can just square these guys. Square, 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 square. So that will be m times, for mvn square, I'm going to Rnf times Rn square equals n square h bar square. So I'll just keep the pi's inside there. This is all constant because I'm in the nth orbit. So the Rn cube is n square h bar square over mf. Then Rn goes as n to the power 2/3 because I take a 1/3 of everything, and these guys are constant. So if you write down Rn is n to the power 2/3 h bar square over mf 1/3. That's Rn. Rn equals to. So we just ruled that out. So it's going to be this, and we just check if n v is like that. Well, we can just check from here. So m vn Rn equals nh bar. So then Vn is nhr bar over m Rn. So here's n, and there will be n to the 2/3 over here. So this will go as n over n to the power 2/3. So this will go as n to the power 1/3. So it's whether we're just checking, not exactly, just proportionality. So it's 1/3. This is correct. So this is correct. So A is not correct, B is correct. Now to look at the energy, we already know what the energy looks like. Energy looks like this. I could go this direction or just go with that. F is constant. Rn is already figured out. So En equals 3/2 Rn is this n to the power 2/3 h bar square, n square h bar square, all the way 1/3 mf times f. So if I bring f inside here, that becomes f cube, because 1/3, and cancel that becomes 2. So n square h bar square 3/2. H bar square will be n square h square f square 4 pi square m 1/3. So this is that guy, and of course this is not 2, so this is correct. Yep. So this was pretty straightforward, but you really had to know what the Bohr model meant. And a lot of students can memorize the Bohr model when the potential energy is coming from electrostatic energy. Over here, they try to trick you. Potential energy is not coming like that. A regular Bohr model is potential energy is equal to Z E square over R. So, and this is not that way. So all the formula that in the books are using this, not going to apply over here. And that's why they really want you to go through this circular motion problem, angular momentum quantization, and then the energy from the fundamental energy formula, kinetic energy versus potential energy. Okay, I will see you in another video. Take care. Bye.